Chapter 15: Organic Compounds and the Atomic Properties of Carbon. In this chapter, we're going to study the special nature of carbon and the characteristics of organic molecules, the structure and classes of hydrocarbons, some important classes of organic reactions, properties and reactivities of common functional groups, synthetic macromolecules and biological macromolecules. Carbon forms covalent bonds in all its elemental forms and compounds. To understand this, let's look at the periodic table. In periodic table, carbon lies at the center of the second row. So, in its electronic configuration, it passes helium, 2 more electrons fill the 2s orbital, and 2 more electrons in the 2p orbital. So here is the electronic configuration of carbon, and the number of valence electrons is 4. To achieve the stable form as helium, the noble gas form, it needs to lose 4 electrons. To achieve the stability structure of neon, it needs to gain actual 4 electrons. In comparison, a metal such as lithium only needs to lose 1 electron to form a cation, or fluorine only needs to gain 1 electron to form an anion. So for carbon, neither forming of cation or anion is favorable, and the formation of carbon ions is therefore energetically unfavorable. Instead, it prefers to share electrons to form covalent bonds. By forming covalent bonds, carbon exhibits catenation, which is the ability to bond to 1 or more carbon atoms and form stable chain, ring, and branched compounds. Carbon has 4 valence electrons. These electrons are in 2s orbital and 2p orbital, and these orbitals hybridize to form 4 bonds in virtually all its compounds. The small size of carbon atom allows it to form short, strong bonds. And these hybridized orbitals not only forms so-called sigma bond, they also forms pi bond. And this increases the variety of compounds that can be formed. Carbon also forms bonds with heteroatoms, atoms other than carbon and hydrogen, such as oxygen, nitrogen, halogens. This type of bonding increases the diversity and the reactivity of organic molecules. And this is because most organic reactions involve the interaction of an electron-rich area in one molecule with an electron-poor site in another. In a carbon-carbon single bond, the electrons equally distributed between the 2 carbon, and the bond is strong. So carbon-carbon single bond is unreactive. Same is for carbon-hydrogen bond. So organic molecules only containing carbon-carbon single bond or carbon-hydrogen bond are unreactive. They don't contribute to the reactivity. On the other hand, if a molecule containing pi bonds are weak, and therefore they make molecules reactive. Or if a molecule containing carbon heteroatom bonds, such as oxygen is more electron negative, so it pulls electron away from carbon, create an imbalance in electron density, and provide a site for reaction to occur. So if a molecule contains pi bonds or carbon heteroatoms, the bonds between carbon heteroatoms, these molecules are reactive. And these molecules, or the groups that containing these pi bonds and the carbon heteroatom bonds, are called functional groups. Because functional groups contribute to the reactivity, they play a central role in organic chemistry. Our discussion begins with the simplest type of organic compound, hydrocarbons. The compounds only contain hydrogen and carbon, and the simplest one is the one with only one carbon. Because each carbon should have 4 bonds, so this carbon must bond to 4 hydrogens. And this is called methane. The next one is the compound with 2 carbon. Okay, these 2 carbon bonds to each other, and because each carbon should have 4 bonds, so now each carbon should have 3 extra bonds that bonds to hydrogen. And this is called ethane. For simplicity, we use carbon skeletons. So using carbon skeletons to show the bonding arrangement of carbon atoms only, leaving off the hydrogen. So ethane, we can simplify it by just carbon-carbon, just to show the arrangement of carbon atoms without hydrogen. Now, when we draw these structures, we should be aware that groups joined by single bond are relatively free to rotate. So this bond can rotate, and we'll see in the next slide. Here shows a hydrocarbon with 5 carbons called the pentane. The black ball indicates carbon. So here's 1 carbon, 2, 3, 4, 5. And each carbon has 3 carbon-hydrogen bonds. So this is 1 hydrogen, and this is 1 pointing out, and this is the 1 pointing back, and another one front, back, front, back, front, back, front, back, and 1 more hydrogen. Now, if we leave off hydrogens, only show carbon-carbon arrangement, we get the skeleton like this. Okay? Now remember, bonds can rotate. The single bonds can rotate. So if the molecule rotates along this bond, okay, let's see how it rotates. Go. Okay, so this is after rotation along this bond. Okay, now if we draw the skeleton, okay, we get this one. So these 2 skeleton, carbon skeleton, although looks different, they represent the same molecule, but they only rotate, the same molecule only rotate along 1 carbon-carbon bond. And molecule not only can rotate along carbon-carbon bonds, it can also rotate along the molecular axis. So if this is the horizontal axis, and the molecule, the whole molecule rotate. Okay, let's see how it rotates. Okay, so this is after rotation along the horizontal axis, and now the skeleton structure becomes this one. Okay, if you rotate along this vertical axis, okay, let's do it. Okay, now here is the skeleton. So all these skeleton structure, although they look different, they represent the same molecule. In the last slide, we showed that carbon-carbon single bond can rotate. So when we draw the structure, they may look different, but they represent the same molecule. And we should focus on arrangement of carbon atoms, and that is the successive linkage of one to another. Okay, so for example, here shows the butane, and the second one and the first one are the same molecule. Okay, the only difference is the rotation. So you rotate along this bond, all right, you get the last one. And if you look at the linkage, carbon 1 connect to carbon 2, and 2 connect to 3, and 3 connect to 4. Same thing is the second one, 1 to 2, 2 to 3, 3 to 4. Now, 3, the third one, okay, is different. The linkage is different. For example, if this is carbon 1, 1 to 2, 2 to 3, but 3 is not to 4. Instead, is 2 to 4. So number 2 carbon connect to 3 and also 4. And so the first and the second molecule cannot become the second molecule by just simply rotation. The bond linkage is different. The last one, okay, 1 to 2, 2 to 3, 2 to 4. So the linkage between the third molecule and the fourth molecule are the same. And therefore, these two are the same molecule. As the total number of carbons increases, the number of different arrangements also increase. Let's take 5 carbons as an example. If a molecule only contains a single bond, we have 3 different types of arrangements of the carbon atoms. Note that the first one is a linear molecule. Now, if we draw the skeleton as here, as this, we know from before, these two are the same molecule. They just look different due to the rotation of the bond, the single bond. But this second one is different because this carbon connect to 3 carbons, 1, 2, 3, while in the first molecule, this carbon only connect to the 2 carbons. And then the third one, this carbon connect to 1, 2, 3, 4. And therefore, this is a different molecule. So we have 3 different arrangements of the carbon atoms. And this is when you have 5 carbons with a single bond. When we have 7 carbons, then we will have 9 different arrangements. And when we have 10 carbons, we'll have 75 different arrangements. And when we have 20 carbons, and this will go to 300,000 ways to arrange the carbon atoms. Now, if we add a double bond, that will even more increase the number of arrangements. For example, here you have double bond can be first one, can be second one, or you arrange carbon differently with the double bond at different locations. And if a molecule contains rings, that will even increase the number of arrangements even more. When drawing carbon skeletons, you need to be aware that each carbon atom can form a maximum of 4 bonds. And this may be 4 single bonds, as shown here, or a double bond and 2 single bonds. So double bond, 2 single bond. So these carbons still have 4 bonds, or a triple bond with a single bond. So again, this carbon has 4 bonds. The arrangement of carbon atoms determines the skeleton. So a straight chain and a bend chain represents the same skeleton as we shown before. Groups joined by a single bond can rotate freely. So a branch pointing down is the same as the one pointing up. So here, let's draw a skeleton. Okay, so note that here we're pointing down, and here, let's draw another one. Okay, this pointing up, but these two are the same because when you rotate, you get the other one. Okay, rotate the carbon-carbon single bond. However, if this bond is a double bond restrict rotation, then the molecule may be different. For example, here, okay, I have a double bond with a bond pointing down, and this one okay, carbon pointing up. These two are different. Okay, these two are different because this double bond cannot rotate. After drawing the carbon atom skeleton, we need to add the hydrogen atom skin to the carbon atom skeleton. So in this skeleton structure, each carbon atom is singly bonded to one other atom. So for example, the second one bonds to one carbon, so that's one bond. Because each carbon should have 4 bonds, and therefore you need to add 3 hydrogens, so that the total number of bonds is 4. So 1, 2, 3, 4. Same thing is for the first carbon. Okay, you already have 1 bond between carbon-carbon, so you also need to add 3 hydrogens. Now in this skeleton structure, the center carbon is connected to 2 other carbons, so 1, 2. In order for this carbon to have 4 bonds, you need to add 2 hydrogens. In this skeleton structure, the center carbon is connected to 3 carbons, 1, 2, 3, and 1 hydrogen is needed. In this structure, the center carbon is already connected to 4 carbons, so it's already fully bonded. No hydrogen atoms are needed. When a molecule contains a double bond, the double bond needs to be treated as if it were bonded to 2 other atoms. For example, in this skeleton structure, this carbon has a double bond, so that means it has 2 bonds to another carbon. And therefore, for 4 bonds, you need 2 hydrogens. In these 2 molecules, the carbon here has a double bond, that's 2 bonds, and also 1 bond to carbon. Okay, and so that's 3 bonds already. So you need 1 hydrogen. And the next one, the carbon has a triple bond, so that's 3 bonds. And therefore, it also needs a hydrogen. So both needs 1 hydrogen to form 4 bonds. Sample problem 15.1. Draw structures that have different atom arrangements for hydrocarbons with A, 6 carbon atoms, no multiple bonds, and no rings. B, 4 carbon atoms, 1 double bond, and no rings. C, 4 carbon atoms, no multiple bonds, and 1 ring. In each case, we draw the longest carbon chain first, and then we work down to smaller chains with branches at different points along them. Then we add hydrogen atoms to give each carbon a total of 4 bonds. In A, it has 6 carbons. Let's start with the 6 carbon chain. So let's draw skeleton. 1, 2, 3, 4, 5, 6. 6 carbon chain. And then we add a hydrogen skin to this skeleton. So the first carbon already have 1 bond. We need to add 3 hydrogens. And the second one, carbon already have 2 bonds. So we need to add 2 hydrogen. All right. And so on, keep going. And here is the structure. Okay. Next, we draw 5 carbon. Okay, we reduce 6 to 5, but because total is 6 carbon, so we need to add 1 more as a branch. So first, let's draw the structure, the skeleton. 1, 2, 3, 4, 5. All right. Now, can we add extra one, the carbon, to here, to the end? Well, if we do, we get the same as the first one. So that's the same. We need to add a different position to get a different arrangement. So maybe we can add here. That's one possibility. Or, okay, we can add a different position. So we can add here. These two are different arrangement. Now you may ask, is there another place that we can add? Can we add here? Well, if you add here, these first one and this one are actually the same, because molecules, they can rotate, they can flip. So if this is the axis, okay, the molecule can rotate so that the right side goes to the left side, and the left side goes to the right side. But it's still the same molecule, same arrangement, but you get this one there. So they are the same, okay? And therefore, if you have 5-carbon chain with 1 branch, and that's the only 2 possible, 1, 2, all right? And then you add a hydrogen skin to this molecule. So you have 2 possible arrangements, 2 molecules with 5 carbon, 1 branch. Okay, let's reduce 5 to 4. Okay, 4 chains and 2 branch. So 1, 2, 3, 4. Again, we cannot add to the end because that will goes to 5-carbon chain. All right. So one possibility is we add a carbon here, another carbon here. That gives you total 6 carbons. Okay, so that's one arrangement. Or we can add 1, 2, 3, 4, and we add 2 carbons, both on one same carbon. So note that these 2 are in the same carbon. So that's another different arrangement. Okay. Now you may ask, can we add both to here? Okay, the second carbon. Well, you get the same molecule because again the molecules rotate. All right, and when you rotate, you will see they are the same. So again, only 2 possible arrangement, and then you add hydrogen skin to the skeletons. Okay. Now what about 3-carbon chain? Can we reduce to 3? So 1, 2, 3, and then you add another 3. Okay. If you do, you will see you will generate the same as we already drawn. Okay, so these are all the possible arrangement. So 1, 2, 3, 4, 5. That's all. In question B, 4 carbon atoms, 1 double bond. First, let's draw 4 carbon chains. Okay, so 1, 2, 3, 4. And then we add a double bond. So the double bond can be on the first carbon. Okay, or let's draw another skeleton and put double bond on the second carbon. Now, can we add double bond to the third one? If we do, these 2 are the same. Okay, again, you can rotate the molecule. You get the same arrangement. Okay, and therefore these are the 2 possible arrangement for 4 carbon chain, 1 double bond. And then you add a hydrogen skin to these skeletons, and you get 2 structures. Okay, so remember, double bond should be treated as 2 bonds. So for this carbon, 2 bonds plus 1 bond here, 2 bond here. So you need 1 hydrogen. Okay, so let's reduce 4 carbon chain to 3 carbon chain. Okay, so we have 1, 2, 3 carbon, and now we need to add another carbon because altogether is 4. So you have to add to the center one. Okay, you cannot add to the end. That will give you the same 4 carbon chain. So then we add a double bond. Now double bond here. Now can we add here? Well, that's the same molecule. Okay, and therefore this is the only structure. Okay, so either here or here or here, they are the same molecule. Okay, and then you add hydrogen skin to the skeleton. Question C, compounds with 4 carbons and 1 ring. Let's start with the longest chain, 4 carbon ring. So let's draw the skeletons, the carbon skeleton, 4 carbon chain. Okay, and then we add a hydrogen skin to it, and so each carbon already have 2 bonds, so we need to add 2 hydrogens. Okay, and so you add 2 hydrogens to all of these 4 carbons. So that's the structure. And now let's draw a smaller ring and 3 carbon ring. So 1, 2, 3, and because the compounds we have 4 carbons, so we need to add 1 more carbon to one of these carbon on the ring. So let's add here. All right, that's the skeleton structure. Now if we add to another carbon, okay, for example here, and then these 2 should be the same arrangement. Or you can add here, you get also the same. So there's only 1 arrangement. And then you add hydrogen to it. Okay? So because 3 carbon ring is the smallest, so that's all we have for compounds with 4 carbon atoms and 1 ring. Let's now discuss alkanes. You already know hydrocarbons contain only carbon and hydrogen. Alkanes are hydrocarbons that contain only single bonds and are referred to as saturated hydrocarbons. Compare with the compounds with double bond, for example here. Okay, and this is called alkene. Okay, note ENE for double bond and ANE for single bonds molecules. So if you have, okay, so here it's carbon. Now if you have a 2 carbon alkane, so then all single bonds. Okay, so compare with this one. For the double bond molecule, there's a potential 2 more hydrogens are added to this one. Okay, and that's why it's called unsaturated. So double bond is unsaturated, but the alkane with only single bond are saturated. Okay, there's no potential to add hydrogen to alkane. The general formula for alkane is CnH2n plus 2. So in this case, the formula is C2H6. And in this case, N is 2. So 2 times N, which is 2, plus 2, and that gives you 6. Alkanes comprise a homologous series, a group of compounds in which each member differs from the next by CH2. For example, if we add 1 more carbon to this molecule, so the 2 ends are the same, hydrogen, okay, so if you compare 2 ends are the same, we just add the CH2. Note here is CH2. Okay, if you want to add more, for example, 4 carbon, again the 2 ends are the same. But 2 carbon hydrogen 2 CH2 are added. The name of any organic compound is comprised of 3 portions: prefix, root, and suffix. The root name of the compound is determined from the number of carbon atoms in the longest continuous chain. For example, if there's only 1 carbon, the root is meth. And if we have 2 carbon, the root is eth. The suffix indicates the type of organic compound and is placed after the root. For example, if this carbon is connected to 4 hydrogens, okay, with a single bond, and we know it's alkane, and the root is A and E, so we add A and E after root meth, and this is called methane. Similarly, if these 2 carbon both connect to hydrogen with a single bond, and this is alkane, and therefore we add A and E as its suffix. So the name is ethane. Okay. Each prefix identifies a group attached to the main chain as well as its position. In these two examples, prefix is not necessary. Here shows some numerical roots for carbon chains and branches. For one carbon, the root is meth. If it's alkane, it's called methane, A-N-E. For two carbons, it's called eth. The root is eth. So if it's alkane, it's called ethane. 3 carbons, propane. 4 carbons, butane, so but. 5 carbon, pentane. 6 carbon, hexane. 7 carbon, so heptane. 8 carbon, octane. 9 carbon, nonane. 10 carbon, decane. Rules for naming an organic compound. Number 1, name the longest chain. Let's use this molecule as an example. First, find the longest continuous chain of carbon atoms. If you look at this molecule, you may find different chains. So you need to find the longest one. For example, here is one chain. If you count the number of carbon atoms, you will find 6 carbon atoms. Or you can go this way. Okay, if you count number of carbon atoms, it's 5, and therefore the longest chain should be 6. Okay, and then we select the root that corresponds to the number of carbon atoms. In this case, it should be hex for 6 carbon atoms. Okay, number 2, name the compound type or suffix. For alkanes, add the suffix A and E. So this is a alkane, and therefore we add A and E. So it's called hexane because the longest chain has 6 carbons. Okay, if the chain forms a ring, then we need to add cyclo to indicate it has a ring. But this molecule doesn't have a ring. Okay, so we don't need to add a cyclo. And number 3, name the branches. Okay, so if this is the main chain, then these are the branches. Okay, we need to find the name for each of these branch. So for this one, only 1 carbon. So 1 carbon, the root should be meth. Okay, to show it's a chain, it's a branch, we need to add YL. Okay, YL to indicate it's a branch. So here, this is called methyl. Okay, meth plus YL, and this has 2 carbon, so it should be eth, and then plus YL is called ethyl. So 2 branches, and then the branch names precede the chain name. And if you have 2 branches, the name appear in alphabetical order. So ethyl should be in front of methyl by alphabetical order. And therefore we have ethyl, methyl, hexane. So the main chain is hexane. Ethyl, methyl are 2 branches. Okay, next, to specify where a branch occurs along the chain. To do that, we need to number the main chain carbon atoms consecutively, start at the end closer to the first branch. So we can number 1, 2, 3, 4, 5, 6. Okay, when we name this way, the first branch methyl is at number 2 carbon. Now, if we go the opposite way, for example, 1, 2, 3, 4, 5, 6, then the first branch is here, number 4. It's this ethyl at number 4 carbon. Okay, we need to achieve the lowest number for the branch, and therefore this way, from left to right, is the correct way, because the first branch is number 2, the lowest. Okay, and therefore we see methyl is at number 2 carbon, ethyl is number 3, okay, carbon, and therefore the name is 3-ethyl, okay, because ethyl is at number 3 carbon, so 3 carbon ethyl, 2-methyl hexane. So the main chain is hexane, but at number 3 we have ethyl, number 2 we have a methyl. And note that we add a hyphen between the number and the prefix, the branch. Okay, so 3-ethyl, 2-methyl. And between the branch, the prefix, and the root hex, there's no space, so methyl hexane. Chemists designed different ways to depict organic compounds. Let's use 3-ethyl 2-methyl hexane as an example, the molecule we showed in the last slide. Here is the condensed formula. In this formula, we write CH3 to represent a carbon with 3 hydrogens. It does not show the bonds. In an expanded formula, this carbon shows 3 carbon hydrogen bonds. So 1, 2, 3. All right. Similarly, in condensed formula, here we have CH2. It doesn't show the bonds, but in expanded formula, this carbon has 2 carbon hydrogen bonds, so 1 and 2. Now, in expanded formula, all these bonds look like 90 degree. In reality, are those bonds 90 degree? The answer is no. So in fact, it's called tetrahedron geometry. So tetrahedron geometry, and this is better represented in a ball and a stick model. So if you look at this, okay, CH3, one hydrogen, this one pointing in front, and these two, this one on the back, okay, and the angle is 109 degrees. So these angles are all about 109 degrees. Same thing is this carbon. So you have carbon, 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 carbon bonds, and there's a hydrogen here pointing backwards. Okay, so ball and stick model is better to show the angles of the carbon, 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 hydrogen bonds. Okay, now if we remove or omit all these hydrogen atoms, just show the carbon-carbon arrangement, okay, you will get this called the carbon skeleton formula. And in carbon skeleton formula, we omit all the hydrogens and the carbons. So each line represents a bond, carbon-carbon bond. So here the end means there's a carbon here. So here carbon here, and the intersection also a carbon. So the end a carbon, intersection a carbon. So basically it shows all the carbon-carbon arrangement, but omit all hydrogens and the symbol carbon symbols. And you can see the carbon-carbon arrangement is a zigzag arrangement, just like here ball and stick model, okay, because the angle here is 109 degree. Now the last one is called the space filling model, and this is better to show the relative size of the atoms. So here inside is a big carbon atom, and the blue one are the hydrogen atoms, much smaller than the carbon atom. This diagram shows some cycloalkanes. The smallest one is cyclopropane. So we have 3 carbon, and therefore it's propane, and it's a ring, so you add a cyclo, so called cyclopropane. And this is the skeleton structure, where we omit all hydrogens and the symbol of carbons, only show the carbon-carbon bonds, so 3 carbon-carbon bonds. And this is a carbon. Because this carbon already have 2 bonds, so you need to add 2 hydrogen. That's why you have 2 hydrogen. So this is the expanded formula for cyclopropane. And this is the ball stick model, which is better to show the angles of those bonds. And the next one is cyclobutane, 4 carbon, so butane, and it's a ring, so cyclobutane. Again, this carbon has 2 bonds, so you need to add 2 hydrogen. Okay, so that this is the extended formula, and then the ball stick model, the space filling model for cyclobutane. Cyclopentane, 5 carbon ring, and again for extended formula you need to add 2 hydrogens so that each carbon has 4 bonds. And this one is a cyclohexane, so 6 carbon, a ring, that's why it says cyclohexane. And then each carbon needs 2 hydrogen to make 4 bonds. Alright, so extended formula, ball stick model, and space filling model. Sometimes 2 different molecules may have the same formula, and these are called isomers. For example, butane contains 4 carbon, so you have 1, 2, 3, 4, and let's add hydrogen. Okay, so this is butane with 4 carbon atoms. Okay, the formula is C4H10. Okay, if you count hydrogens, there are 10 hydrogens here. Now, so there's another molecule, okay, also 4 carbon, okay, but this carbon is attached to the center carbon. So now let's add hydrogen. Okay. All right. Now, if you count hydrogens, there's also 10 hydrogens. So 4 carbon, 10 hydrogens. Formula the same, but the arrangement are different. So here, carbon 1, 2, 3, 4. It's a chain. But here is a branch 1, 2, 3. And 4. So number 4 is attached to number 2. So they have different arrangements. And therefore, these 2 are different molecules. And they are called isomers. And because the structure are different, they have different structures. And therefore, these are called constitutional or structural isomers. Now, a straight chain, alkane, may have many branched structure isomers. In this case, for butane chain, there's only one, so one branched isomer. Now, if we have 5 carbon, we'll show you later that 5 carbon chain have 2 branched isomers. Structure isomers are different compounds, so these 2 are different, and therefore they have different properties. For example, they have different melting point, different boiling point. Okay, so they just completely different molecules, even though they have the same formula. Here shows the constitutional isomers of butane and pentane. So this is the expanded formula of butane, and condensed formula, skeleton formula. And this is the isomer, okay, with a branch here. This is the, again, condensed formula, and the skeleton formula shows the branch here. And you can see they are different molecules, and they have different density. Okay, one is 0.579, one is 0.549, and the boiling point are different. One is negative 0.5, one is negative 11.6. Okay, here we show pentane, so 5-carbon chain, all right, condensed formula and skeleton formula, and 2 isomers, okay, 1 branch and 2 branch, okay, they all have the same formula. So if you count carbon 5 and hydrogen 12, so all these 3, they have the same formula, but they have different structure. They are constitutional isomers, and they have different density, they have different boiling point, they are different molecules. Alkanes are nonpolar, and their properties are determined by the dispersion force. Okay, let's take methane as an example. So carbon with hydrogen, okay, 4 of them. Okay, because carbon and hydrogen have similar electronegativity, so the carbon-hydrogen bond is nonpolar, means the electrons are equally shared between carbon and hydrogen. However, at any instant, the electrons fluctuate between the carbon and hydrogen. So at one point, the electron may go towards carbon more than hydrogen and make hydrogen partially positive and the carbon partially negative. At the same instant, there's a neighboring methane, okay, here, and these 2 electrons also fluctuate towards the hydrogen, so the hydrogen becomes partially negative and the carbon becomes partially positive. So this partially positive carbon, hydrogen, partially negative hydrogen, they attract each other because of different charge. Okay, so that's at one instant, but because the bonds are nonpolar, so the electron fluctuate at the next instant. The electron may fluctuate to the hydrogen for the first molecule, but then for the second molecule, the 2 electrons fluctuate to the carbon. So again, one is partially negative, the other partially positive. Again, they attract each other. So this kind of attraction force is called dispersion force. Okay, it's due to the instantaneous fluctuation of the electrons. All right, and the one important property of the dispersion force is that the larger the molecule, or the heavier the molecule, the larger the dispersion force. So methane has a small dispersion force. Ethane has a larger dispersion force. Propane has even higher dispersion force. So when you increase the number of carbon, the dispersion force increase. In order to evaporate the molecules, you need to increase the energy to break the dispersion force, and therefore you need a higher temperature. So the boiling point increase when the number of carbons increase. For methane, boiling point is negative 164. Ethane, only negative 89. And then when you increase number of carbon, the boiling point increase. And for decane, okay, 10 carbon atoms, the dispersion force are so large, you need 174 degrees to evaporate the molecules. A hydrocarbon that contains at least one carbon-carbon bond, double bond, is called an alkene. Here are 3 examples. They all have a double bond. Alkenes are unsaturated and have the general formula CnH2n. Let's look at the first molecule. If we replace this double bond by a single bond, carbon-carbon single bond, okay, then the 2 carbons now only have 3 bonds, and we need to add 1 more bond. So carbon-hydrogen bond, carbon-hydrogen bond. Okay, and this is an alkane, ANE. So alkene can add 2 hydrogens to form an alkane, and therefore alkene is unsaturated. More hydrogens can be added, and the formula for alkane, ANE, is CnH2n plus 2, and for alkene it should be Cn2n. There are 2 hydrogens more in ANE than ENE. Okay, alkane has 2 more hydrogens because of the double bond. To name an alkene, the root name is determined by the number of carbon atoms in the longest chain. So that's similar to alkane, but it also must contain the double bond. All right, so let's look at the first molecule. Okay, so this molecule, the longest chain contains the double bond is 4. So 4 carbon, and therefore the root should be but, B-U-T, and the suffix is ene because you have a double bond, so it's called butene. Okay, we should also number the carbon atoms. Okay, we should number of the carbon atoms from right to the left. Okay, because this will make double bond the closest to the end. So this is number 1 carbon has a double bond, number 2, and 3, and 4. If we go from left to right, okay, that will put double bond at the number 3 carbon. Okay, so that's not the correct way. And therefore, the full name should be 1-butene. 1, okay, tells you it is at the number 1 carbon that has the double bond. And the total is 4 carbon, so but, and it's a in, so 1-butene. Okay, now usually if the double bond is at the number 1 carbon, this number 1 can be omitted, so we can also call this just butene. All right, if the double bond is not at the number 1 carbon, we must add the prefix, okay, number in front of the name. So let's look at the second molecule. It also has 4 carbon atoms, so it's also a butene because it has a double bond. Now if we number the carbon atoms, okay, so 1, 2, 3, 4. So the double bond is at the number 2 carbon. If you number from right to left, you get the same number, also number 2. Okay, and therefore the name for this one should be 2-butene. Okay, number 2 carbon has a double bond, and the total is 4, so butene. Okay, in this case we cannot omit number 2. We must add 2-butene. Okay, next one, the longest chain containing the double bond has 3 carbon atoms, so it should be prop, P-R-O-P, and it has a double bond, so it's propene. All right, and if we number the carbon atoms, we must go from left to right to left to make the double bond closest to the end. So this is number 1, number 2, number 3. Okay, number 1 has a double bond, so we can omit 1. Okay, we just say propene. And number 2 has a alkyl group, this alkyl group only have one carbon, so it's called methyl. Okay, so the name should be 2-methyl. Okay, number 2 carbon has a methyl, and the main chain has 3 carbon with the double bond, so propene. So 2-methyl propene. In the last molecule, the number 1 carbon has a double bond, so the full name can be named 2-methyl 1-propene. Okay, so this number 2 tells you the methyl group is at number 2 carbon. So this is 1, this is 2, and the 1 here tells you the double bond is at number 1 carbon. So 2-methyl 1-propene. Now this, of course, as we mentioned, if double bond is at the number 1 carbon, this 1 can be omitted, and therefore we can simply say 2-methyl propene. The double bond of an alkene restricts rotation so that the relative positions of the atoms attached to the double bond are fixed. Let's use butane as an example. So the first molecule has 4 carbon, so 1, 2, 3, 4, and therefore it's a butane, has a double bond. And the double bond is at the number 2 carbon, so the name is 2-butane. Now the next molecule also have 4 carbon atoms, 1, 2, 3, 4. And the double bond also at the number 2 carbon, so the name here, names are the same, also 2-butane. But if you look at the structure, they actually are different. In the first molecule, these 2 ends pointing to the same side, okay? But in the second molecule, these 2 ends are opposite side, all right? Now, if it's an alkane without double bond, okay, let's draw this. So if we have a molecule, butane, so if we draw like this one, this is a skeleton, all right, just draw the skeleton. Or if we draw another one, only single bond, okay, are the same or different? Well, they are the same because this bond can rotate. If you rotate it, this carbon will go down. So for a single bond, it can rotate, and therefore these 2 are the same molecule. But because of the double bond cannot rotate, all right, restrict the rotation, and therefore the relative position of atoms attached to the double bond are fixed. So they are fixed, and therefore this molecule is different from this molecule, and they called geometric or cis-trans isomers. When the 2 ends at the same side is called a cis isomer, and when the 2 ends are opposite sides, and this is called a trans isomer. So the first molecule name should be cis-2-butane, and the second one is trans-2-butane. The geometric isomers have different physical properties. So they have different density, they have different boiling point, they are different molecules. An alkyne is a hydrocarbon that contains at least one carbon-carbon triple bond. The suffix is YNE. So this one has 4 carbon with a triple bond. It's called butane. Compared with butane, it has 2 fewer hydrogens. And butane has 2 fewer hydrogens than butane. So the general formula for alkane is CnH2n plus 2. For butane is for alkene is CnH2n. And for alkyne is CnH2n minus 2. Sample problem 15.2. Give the systematic name for each of the following and draw two geometrical isomers for part E. So in A, you can see all bonds are single bonds. If you look at the first carbon, it has 3 hydrogen. That means it forms 3 carbon-hydrogen bonds with 1 carbon-carbon bonds. So that's 4 single bonds. Same thing is for this carbon, this carbon, this carbon. And this one has 2 hydrogen bonds, carbon-hydrogen bond with 2 carbon-carbon bonds. So all bonds are single. There's only carbon-hydrogen, so this is an alkene. So the root is A and E. And the longest chain is 4. Okay, if we go this way, you have 1, 2, 3, 4. Okay, and the closest alkyl group is number 2. If you go this way, you will put the alkyl group number 3. And so we should go from left to right. And so the main chain is 4, so it's a butane. Okay, butane, and number 2 have 2 alkyl groups, methyl. So this is a methyl, and this is also methyl. When we have 2 same alkyl group in the same molecule, we use dimethyl. Okay, if we have 3 same group, we use tri. Okay, so in this case, you have number 2, so 2. Okay, so 2 dimethyl butane. Okay, why you have 2? Because you have 2 alkyl groups. So 2 methyl and 2 methyl, and you combine together, say dimethyl. So 2 dimethyl butane. Okay, so that's the A. Let's look at B. B is similar to A, which is an alkane, and so all single bonds. So the root is A and E, and the longest chain is 6. So if you look at here, 1, 2, 3, 4. Okay, maybe you think it's 5, but in fact, if you go this way, 5, 6. So this way is the longest chain instead of go straight. Okay, you need to find the longest chain. So here should be 6. Okay, and number 3 has a methyl group. Number 4 has a methyl group. Now you may also go this way. If you go this way, you also put number 3, number 4, 2 alkyl groups. So that gives you the same name. All right. So again, you have 2 methyl. Okay, 2 methyl. So it should be dimethyl, and it's number 3 and number 4. So 3, 4 dimethyl hexane. All right. So longest chain hexane. 2 methyl groups, dimethyl, number 3 and number 4. Okay, 3, 4. Compared to the first one is 2 and 2, so 2, 2 dimethyl. Now in number C, question C, we see a ring. So and also 5 carbon. 5 carbon means it's a pentane, and whenever you see a ring, it's a cyclo. So cyclopentane, and then you need to number it. When you number it, you number from one of the alkyl group. So this is a methyl attached to the ring, and this is ethyl. Okay, we use alphabetical order. So ethyl is before methyl. So you go this way, 1, okay, 2, so that the number is the smallest for the methyl group, alkyl groups. So 1, 2, 3, 4, and 5. So 1 ethyl, 2 methyl, cyclopentane. Okay. Now if you go this way, so that would be 1 methyl, 2 ethyl, but the ethyl should be in front of methyl because alphabetical order. Okay. So next one in D, we see a double bond, so that root becomes in, E-N-E, alkene. Okay, and the longest chain is here. That's 1, 2, 3, 4, 5. So it should be pentene. So pentene, and we should label it. The label must make sure the double bond has the lowest number. So you should go from right to left. And so 1, 2, 3, 4, 5. Okay, and therefore it's 1. So it's 1 pentene. And number 3 has a methyl group. So 3 methyl, 1 pentene. Okay, now you can omit 1 because 1 is in front, is the double bond is number 1. So you may say 3 methyl pentene. Okay, and let's look at E. Okay, question E. Now in question E is again a double bond. So and the longest chain is 1. So this 1, 2, 3, 4, 5, 6. So should be hexene. E-N-E. Okay, hex means 6. So hexene. And where is the number bond, double bond? So you need to label it. If you go from left to right, you get 1, 2, 3, 4, 5, 6. So number 4, number 5 have 2 methyl group. Now if you go from right to left, okay, so 1, 2, 3, 4, 5, 6. Now this way you have number 2 methyl, number 3. So that will give lowest number of alkyl groups. So we should go from right to left instead of from left to right. Okay, and because both are methyl, we can combine together, say dimethyl. Say 2, 3 dimethyl, and the double bond is in number 3. So 3 hexene. So 2, 3 dimethyl, and number 3 has a double bond, so hexene. Okay, so that's the name if we only look at this molecule. Okay, now the question says draw 2 geometric isomer. Okay, the geometric isomer, because double bond cannot rotate, and so one possible is CH3, CH2, C, double bond, C, and then C, let's see, CH3, and here you have CH, CH3, and the CH. Okay, and here you have hydrogen. Okay, so this carbon has a metal and a hydrogen here. Okay, because the double bond cannot rotate, so the hydrogen and the metal pointing in the same direction, and it's a fixed position. And if you compare the left side two alkyl groups, okay, one is ethyl group, okay, one is hydrogen. So hydrogen is smaller. So this, let's say this is 1. Hydrogen is small, 1. Ethyl, let's say 2. So smaller. And the right side, methyl is small. So let's give smaller one 1. And this group is bigger. So let's say this is 2. All right. So the smaller one on the left side and the smaller one on the right side are in the same side, and so that is cis. Okay, cis means the two sides, the two groups at the same sides. So if both smaller group are at the same side, is called cis. All right. Now, if this hydrogen is down, okay, then you can see here, this is small. Let's say this is 1. So the smaller one and the of the left side and the smaller one on the right side are opposite. Okay, same thing is larger one are opposite in this case, and that will give you a trans. So 2,3 dimethyl 3 hexane. Okay, so there are two geometrical isomers if you have a double bond. Okay, one is cis, one is trans. Let's talk about types of organic reactions. And the first one is addition reaction. An addition reaction occurs when an unsaturated reactant becomes a saturated product. As you already know, a carbon-carbon double bond is unsaturated, and so is carbon-oxygen double bond and the carbon-carbon triple bond. Now let's look closer at a carbon-carbon double bond. Okay, so two carbon, and each one may have other bonds. So these bonds are single bond. Single bond are also called a sigma bond. Okay, so maybe have more carbon, so carbon-carbon single bond called a sigma bond. Now what about the double bond? Double bond has two bonds. One of them is also a sigma bond. The other one is called a pi bond. So in a double bond, the two bonds are not actually same. So one is sigma bond, one is pi bond. Pi bond is weaker than sigma bond. So during the reaction, is this pi bond that can break. So remember, each bond formed by two electrons sharing between two carbon. So when this pi bond break, okay, let's draw again. All right, so the pi bond break, the two electrons may go to one of the carbon, and the other one has no electron. And therefore, when you have a polar molecule, for example, hydrogen chloride, in the solution, hydrogen chloride immediately becomes a proton and a chloride ion. And the proton has no electron, so it's attracted to the carbon with two electrons. And the chloride has a negative charge, so this is attracted to the carbon that has no electron. And therefore, it forms a saturated compound where chlorine adds to one carbon and hydrogen adds to another. And the double bond is replaced, okay, the pi bond is replaced by two single bond. One is carbon chlorine, one is carbon hydrogen. So here shows the general equation for the addition reaction. The R represents any alkyl groups, so it can be methyl group, so CH3, or ethyl group, or any number of carbon groups. And the purpose is just focus on the double bond and use R to represent the rest of the molecule. Okay, and you can see that when the double bond alkene with a double bond react with a polar molecule XY, represents a polar molecule like hydrogen chloride. X goes to one carbon, and Y goes to another carbon, and the double bond now becomes a single bond here. Okay, the pi bond, okay, is broken and replaced by two carbon X, carbon Y sigma bonds. The reaction between double bond and the bromine addition reaction can be used as a color test for the existence of a carbon-carbon double bond. The bromine liquid has a color orange-brown. When the bromine liquid is added to a solution with no double bond, the solution turns into orange-brown color. On the other hand, when bromine is added to a solution containing this double bond, the reaction takes place and the bromine is consumed, and therefore you can see that the color disappear. The orange-brown color of the bromine liquid disappear inside the solution, and that indicates the existence of a double bond in the solution. A second type of organic reaction is called elimination reaction. Remember, a double bond can undergo addition reaction. So you add HCl, and the pi bond break, okay, forms a single bond, and then 2 bonds added. One is hydrogen, one is chlorine. So this is called addition reaction. Okay, now the reverse reaction is the elimination reaction. So in elimination reaction, the reactants is the saturated compound with a single bond, and this comes off as HCl, as a small molecule. At the same time, carbon-carbon single bond becomes double bond. Okay, so elimination reaction occurs when a saturated reactant, so this is the saturated reactant, becomes a unsaturated product, and this is the reverse of addition reaction. And in general, we can write a saturated molecule, a small molecule XY comes off, and the molecule becomes a double bond reaction. Here shows an example of elimination reaction. And this reactant is a saturated compound called alcohol with a hydroxy group. And during the reaction, this hydroxy group and an adjacent hydrogen come off as a water molecule. And the carbon-carbon single bond becomes carbon-carbon double bond. And so the reaction eliminates a small molecule water and forms an unsaturated compound, alkene. Now, for elimination reaction, usually sulfuric acid is used. Sulfuric acid is called catalyst in this reaction. And the catalyst is a compound that is not consumed itself during the reaction, but it can increase the reaction rate and make reaction go faster. And the driving force for elimination reaction is the formation of small molecules. In the last example is HCl eliminated, and in this reaction it's water. So this small stable molecule can be eliminated. At the same time, a double bond is formed. The third type of organic reaction is called the substitution reaction. A substitution reaction occurs when an atom or group, so in the equation is this Y group, substitute for one, so X, substitute X, which is attached to carbon. And so, in other words, X is replaced by Y. Okay. Here shows an example of substitution reaction. So one of the reactants is called acid chloride. So this is a CO double bond with a chlorine, and this is an alcohol with a hydroxy group. Okay. Now let's compare the reactants and the product. Okay. So in the product, let's label this group as A. So the first reactant is group A with chlorine. And the second group reactants is an alcohol. So let's label this one group as B with hydrogen. So the alcohol is hydrogen attached group B. Now if we look at the product, okay, this is just the group A, same group A, and the other part is group B. So what happens is the group B from alcohol, okay, replace chlorine or substitute for chlorine in A and forms the product. So the product here is called an ester. An ester is formed by substitution reaction between an alcohol and acid chloride. So part of the alcohol molecule replace chlorine in acid chloride to form ester. And this ester is the main flavor ingredient in banana oil. Sample problem 15.3. State whether each reaction is an addition, elimination, or substitution reaction. In the first one, if you compare reactants and the product, so reactants has an actual bromine, and so the bromine must come off. And also, the second carbon, hydrogen, so this is a CH2, but the product is CH. So one of the hydrogen also come off. So the bromine and the hydrogen come off as a small molecule, HBr. At the same time, the two carbon forms a double bond. Okay, so that's the elimination reaction. To eliminate a small molecule at the same time forms a alkene, double bond, unsaturated product. Now, the second one, it's easier if we draw hydrogen. So this is a carbon. This carbon has 3 bonds here, shows 3 bonds, 1 double bond, 1 single bond. So there's 1 hydrogen here, and there's this one also 1 hydrogen here. Okay, now let's look at the product. So this carbon only have 2 bonds, 2 carbon-carbon bonds. So you need to add 2 hydrogen, and same thing is here. Okay, so you can see a double bond add hydrogen, so forms 2 carbon-hydrogen bonds, and that's addition reaction. Addition reaction is a small molecule. Okay, so you can think about hydrogen, hydrogen, and they add to the 2 carbon. Okay, pi bond is replaced by 2 carbon-hydrogen bonds. Okay, next one. So if you label this one group product, okay, they are the same, and the difference is bromine is replaced by this group. Okay, so this is B, all right, and this is A. So chlorine, bromine is replaced by B, and this is substitution reaction. Organic compounds are classified according to their functional groups. A group of atoms bonded in a particular way. For example, if CH is attached to OH, and this is called alcohol, so OH is a functional group. C2H5 attached to OH, again, it's alcohol. So OH attached to alkyl group is alcohol functional group. So it can be C3H7OH. So these are all alcohols. Okay, alkyl groups attached to hydroxy. That's called alcohol functional group. The functional groups in a compound determine both its physical property and its chemical reactivity. Functional groups affect the polarity of a compound and therefore determine the intermolecular force, and that's the physical property. Functional groups define the regions of high-low electron density in a compound and therefore determine its reactivity. Let's start with alcohol functional group. The functional group consists of a carbon bonded to an OH. Alcohols are named by replacing E at the end of parent hydrocarbon name with the suffix OL. Okay, so let's start with simplest one, 1 carbon. So 1 carbon with hydrogen is methane. Okay, now if we replace 1 hydrogen by OH, this becomes alcohol. And the name is we replace the E by OL. Okay, so it's called methanol. Okay, if we have 2 carbon, all right, so 2 carbon, this should be ethane, so ethane. Okay, now if we replace 1 hydrogen by OH, that becomes alcohol called ethanol. Okay, replace E by OL. Alcohols have high melting point and boiling point since they form hydrogen bond, because the bond, carbon-oxygen bond, is polar. So it's so polar that oxygen-hydrogen bond. Okay, so this bond is polar. This let me draw again. So here OH. So this is negative, and this is positive. And so this positive hydrogen interact with a neighboring oxygen. Okay, so CH2, CH3, for example, here hydrogen. So the oxygen is negative, the hydrogen is positive. So a positive hydrogen, a negative oxygen on a neighboring molecule interact, and this is called a hydrogen bond. And this bond is quite strong, and therefore it gives high melting point, high boiling point. Alcohols are saturated compounds, and they usually undergo elimination reaction and substitution reaction. In the first example, the hydroxy group and a hydrogen of an adjacent carbon are eliminated, forms a small water molecule. At the same time, the two carbon forms a carbon-carbon double bond. Okay, so that's an elimination reaction. In the next secondary reaction, the hydrogen attached to oxygen and another hydrogen attached to the adjacent carbon are eliminated. And so oxygen carbon forms a double bond, so-called CO double bond. And this type of elimination reaction is also called oxidation in organic chemistry. So CO double bond becomes CO single bond becomes CO double bond, and that's a oxidation reaction. Similarly, in the third example, the hydrogen attached to oxygen and the hydrogen attached to the adjacent carbon are eliminated and form a CO double bond. That's this type of elimination. Again, is an oxidation reaction. The last one is a substitution reaction. So in this alcohol, okay, the OH functional group is replaced by bromine, forms alkyl bromide, and that's a substitution reaction. When carbon is attached to OH, it's called alcohol. When carbon is attached to a halogen atom, which can be chlorine, bromine, iodine, it's called haloalkene or alkyl halides. For example, when methyl is attached to chlorine, and this is a haloalkene, or it's called chloromethane. Okay, so haloalkenes are named by identifying the halogen, in this case is chlorine, with a prefix. So chlorine is, okay, this is chlorine, okay, becomes a prefix, we change to chloro, okay, INE becomes O, chloromethane. Okay, so chloromethane. Similar to alcohols, haloalkenes undergo substitution reaction and elimination reaction. In the first example, the reactant has 4 carbon, and so it's called butane. And there's a bromine here as a prefix. It's called bromobutane. Bromine is at number 1 carbon, so 1 bromobutane. The other reactant is hydroxide. Hydroxide may come from potassium hydroxide or sodium hydroxide. And when these two reactants mix, hydroxide may substitute bromine to form alcohol. So forms a 1-butanol. So the reaction is a substitution reaction. So bromine is substituted by hydroxide. In the next reaction, the second example, it's a chloroalkene, and the longest chain has 3 carbons, 1, 2, 3, and chlorine on number 2 carbon, so 2 chloro, and methyl group also on number 2, so 2 methyl propane. Okay, the other reactant is potassium ethoxide, And this is very similar to potassium hydroxide, but the hydrogen is replaced by a alkyl group. Okay, and so it's still a strong base, just like potassium hydroxide. And this strong base may eliminate a hydrogen from carbon. So here, CH2 carbon has hydrogen. The hydrogen can be eliminated by this base. At the same time, chlorine is also eliminated, so forms hydrogen chloride, and the carbon-carbon single bond becomes carbon-carbon double bond. And the hydrogen chloride is an acid. It reacts with this base and forms this product. Okay, so the main transformation is the carbon-carbon single bond becomes carbon-carbon double bond, and a small molecule is eliminated. So the reaction is elimination reaction. When carbon is bonded to a nitrogen atom, the functional group amine is formed. The systematic name for an amine is formed by dropping the final E of alkane and adding the suffix amine. However, the common names for amines are also widely used. Common names use the name of a alkyl group followed by suffix amine. For example, the smallest one carbon. So this is methane. And when one hydrogen is replaced by NH2, okay, so a nitrogen, this is called a methylamine. So let me write methylamine. Okay, so use carbon as an alkyl group. So alkyl group is a methyl, so methylamine. Now similarly, if we have two carbon, so this is ethane. All right. Now, if one hydrogen is replaced by a nitrogen, NH2, so the name is ethyl amine. As we explained before, R represents an alkyl group. For example, it can be methyl group, C hydrogen. So that's a methyl group attached to nitrogen. Or it can be ethyl group, so two carbon. Attached to nitrogen, okay? Or a propyl. However, in any event, the nitrogen is attached to only one carbon. So nitrogen, one carbon, one carbon. Now if you add more carbon, so propyl, the nitrogen is attached to still only one carbon. And the other two, the nitrogen attached to, are hydrogens. And in this case, this is called a primary amine. Okay, primary amine is when nitrogen attached to one carbon. In the second one, the nitrogen attached to two alkyl group. That means it attached to two carbon atoms. The third one is a hydrogen. And this is called a secondary amine. When nitrogen is attached to three carbons, and that's called a tertiary amine. In all these amines, nitrogen contains a lone pair electron. Okay, this lone pair electron is important for the nitrogen to have its own reactivity and properties, chemical properties. For example, this makes amines basic, so it can accept positive charged proton. Okay. In fact, it not only attack a positive charged proton, it can also attack positive charged carbon, and that make it nucleophilic. Similar to alcohols, primary and secondary amines can form hydrogen bond. So let's look at methylamine. Okay, so here is a methylamine, and because nitrogen-hydrogen bond is highly polarized, so nitrogen is negative, hydrogen is positive, and there's a neighboring molecule with nitrogen, 2 hydrogen, and methyl. Okay, so this nitrogen also negative, hydrogen positive. So the positive hydrogen on one molecule and the negative charged nitrogen on an adjacent molecule strongly attract each other, and this is called a hydrogen bond. Now, due to the hydrogen bond, amines have higher melting point and boiling points than hydrocarbons or alkyl halides of similar mass. On the other hand, a tertiary amine, okay, amine have 3 nitrogen attached to 3 carbon. So nitrogen only can form 3 bonds with a lone pair electron. So if nitrogen attached 3 carbon, it does not have a hydrogen, and therefore it cannot form hydrogen bond. Amines of low molar mass are usually fishy smelling, water soluble, and weakly basic. Amines undergo a variety of reactions, including substitution reactions. Sample problem 15.4. Determine the reaction type and predict the products for each reaction. To solve this problem, we need to first determine the functional groups of the reactants, and then examine any inorganic reagents to decide on the reaction type. But keep in mind that in general, these functional groups that we have discussed so far undergo 2 reactions, substitution reaction or elimination reaction. In A, the reactants are iodo-propane, sodium hydroxide. The hydroxide from sodium hydroxide may substitute iodine. So the reaction is a substitution reaction, and here write the product. Note hydroxide replaced iodine, so make an alcohol, and the iodide with sodium form sodium iodide salt. So next one is a bromoethane and a amine, so that's a propylamine. So again, the amine has a lone pair electron, it can replace the bromine, so it's another substitution reaction. So amine replace bromine. Okay, so the product, and you can see this comes from the bromoethane, so this part. Okay, and so if this is A, all right, and the amine lose 1 hydrogen. Okay, so that's the B. So it replaces bromine, and then bromine come off actually with 1 more hydrogen and react with another amine. So that's why in the reactants you have 2 amines, one used to substitute bromine, the other react with hydrogen bromide coming off from the reactants, so give you ammonium salt. Okay, so let's look at the next one. Next one is an alcohol. So under this condition, chromate and concentrate sulfuric acid, the reaction undergo elimination reaction. It eliminates 2 hydrogen, form CO double bond. So the reaction is also called oxidation reaction because the CO double bond is formed. Hydrocarbons containing carbon-carbon double bond are called alkenes. Alkenes are unsaturated, so it typically undergo addition reaction, as we shown before. The double bond has 4 electrons, so it's electron rich. And if you have acid such as hydrochloric acid, it has proton, it has chloride ion. So the proton react with the pi bond, okay, because electron rich, so it forms a carbon-hydrogen bond, a new carbon-hydrogen bond, and at the same time, the other carbon becomes positive charged, and the chloride ion will react with this carbon and forms a carbon chloride ion bond. So the net effect is that hydrogen chloride adds to carbon-carbon double bond to form carbon chloride bond, carbon hydrogen bond. So it's an addition reaction. Now, if the acid is dilute, okay, so in a dilute acidic solution, the proton first adds to one of the carbon double bond, from CH2 becomes CH3, and then because the solution has a small amount of chloride, because it's dilute, and therefore it's not the chloride attack the other carbon, instead it's water. Okay, so the oxygen attack carbon, lose a proton, forms hydroxide. So it's hydrogen adds to one carbon, hydroxide adds to another carbon, and the product is an alcohol. And this happens when a alkene react with dilute acidic solution. We show that hydrocarbons containing carbon-carbon double bonds are called alkenes. There's an exception. A six-membered ring with alternate double bond, single bond is not an alkene. Instead, it's called benzene. So we can draw another resonance structure. Okay, well, we put here double bond to here. So this double bond goes to here, and this double bond goes to here. The actual structure of benzene is the combination of these two. And therefore, these bonds, so 6 bonds are all the same. They are equivalent. So, for example, this bond from, let's say this is a carbon 1, this is a carbon 2, and here carbon 1, carbon 2. So the bond between carbon 1, carbon 2 is not a double bond and is not a single bond. It's between these two. And all those bonds are the same. Okay, so in other words, the pi bond electrons are delocalized. It's a resonance hybrid of these two. So one way to represent this is just use a circle to show the pi bond is delocalized among the 6 carbons. Now, because benzene is not simply a combination of 3 double bonds, it's not an alkene, and therefore it does not undergo the reactions as the alkene does. For example, alkenes usually undergo addition reaction, but benzene undergo substitution reaction. So this is a skeleton of benzene, and there should be a hydrogen on each carbon. Okay, when benzene reacts with bromine, so one of the hydrogen is replaced by bromine. So instead of addition, it's a substitution reaction. Benzene is an aromatic hydrocarbon. Although there are other rings also show aromatic properties, benzene is the most common one. Aromatic compounds are usually more stable than corresponding alkenes. A CO double bond is called carbonyl group. When the carbonyl carbon is bonded to at least one hydrogen, and it's called aldehyde. So this molecule, CH3COH, has a carbonyl group. One side has a hydrogen, so it's an aldehyde. And because you have 2 carbon, so it's called ethane. So ethane, and the E is replaced by Al. So ethanol, to represent it's an aldehyde. Okay. Now, when both sides of the carbonyl carbon are carbon atoms, no hydrogen, and this is a ketone. So for example, here you have a ketone. Okay, this is the carbonyl group, and both sides are carbon, no hydrogen, so it's a ketone. And you have 3 carbons, so it's a propane. Now the E is replaced by O and E to represent it's a ketone. Now the carbonyl carbon is at number 1, number 2, so number 2 carbon. So we put 2 here, 2-propanol. Okay. Now this molecule has a common name, acetone. Okay, that's a solvent that you use in the laboratory. We have shown that alcohols undergo elimination reactions. So in this alcohol, the hydrogen of hydroxide and another hydrogen can be eliminated. At the same time, the oxygen combined with a carbon forms a CO double bond. So this reaction, this type of elimination reaction is called oxidation. Okay, because the carbon initially connect only 1 oxygen, and after reaction if connect with 2 oxygen because of the double bond, so it's oxidized. The reaction is oxidation reaction. On the other hand, the opposite reaction is called reduction reaction. So if we start with a CO double bond, and if we add 2 hydrogen, so one adds to carbon, okay, form the CH bond, another adds to oxygen, forms OH, becomes alcohol, and this addition reaction is called reduction reaction. Okay, so ketones, aldehydes undergo reduction reaction. Alcohols undergo the elimination, which is a oxidation reaction. Now, one of the very useful reactions for aldehyde ketones is that they react with organometallic compounds. So here is an organometallic. So R prime is a alkyl group, so it can be CH3. And when this combine with lithium, so lithium a reagent, lithium is a metal, so it always lose electron, so it's a positive charge. And lose electron to carbon, so the carbon is a negative charge. Okay, so in organometallic compound, the alkyl group has a negative charge. Now, if we have a aldehyde or ketone, because of the high electron negativity of oxygen, oxygen has a negative charge, carbon has a positive charge. So you can see these 2 reactants, the carbon in ketones or aldehydes has a positive charge, but in the organometallic compound, the carbon has a negative charge. So these 2 combine, okay, form a bond. You can see this is the carbonyl carbon, so bonds to a new carbon comes from organometallic compounds. So, and the oxygen becomes an alcohol. So ketones, aldehydes react with carbonyl compounds or organometallic compounds, forms an alcohol, and the molecule becomes larger because the organometallic alkyl group goes to the carbonyl carbon. So the molecule becomes larger, and the molecule product is an alcohol. Sample problem 15.5. Fill in the blanks in the following reaction sequence. So for this type of reaction, we should examine the functional group of the reactant and the reagent above the yield arrow to decide on the most likely product. So let's look at the first step. And this is a alkyl halide, okay, bromobutane, and we have a hydroxide. So the reaction is most likely a substitution reaction. The hydroxide replaces bromine. So the product should be, so you copy everything else, but replace bromine. Bromine becomes alcohol, so hydroxide. So that should be this one. Now, Alcohol usually undergo elimination or so mostly elimination, which most time is oxidation. So here, if you see chromate, you know it's oxidation. So the hydrogen, this hydrogen, and this hydrogen can be eliminated, and the CO becomes a double bond. So you have copy everything else. Okay, so CH3, the hydrogen is eliminated, and oxygen becomes a double bond. So alcohol is oxidized, becomes a ketone. Okay, next one this is a organometallic compound. This carbon is a negative charge, and in the ketone, this carbon is positive. So this metal should add to the carbon, and the oxygen becomes alcohol. So the product, this one, you copy everything else. Okay, but the metal from lithium compound adds to this carbon, and the oxygen becomes an alcohol. Okay, so that's the product. Here shows the answer key. So the first step, bromine is replaced by hydroxide to form an alcohol. Okay, next step is elimination, but also called oxidation. So this hydrogen and this hydrogen are eliminated, form a CO double bond. And the next step is the addition of the methyl group to the carbonyl carbon. So you can see it's an alcohol with becomes a larger molecule. If carbonyl carbon is attached to a hydroxide, the functional group is called carboxylic acid. So carbonyl carbon attached to at least one hydrogen is called aldehyde. Carbonyl carbon attached to both carbon, no hydrogen, is called ketones. If one is OH hydroxide, that's a carboxylic acid. Carboxylic acids are named by replacing the E of the alkane with the suffix OIL acid. For example, here is a carboxylic acid, so carbonyl carbon attached to a OH. We have two carbon, and therefore this is ethane, and then we replace E by OIC. So this is called ethanoic acid. Okay, so OIC, ethanoic acid. Carboxylic acid are weak acids in water, so it reacts with sodium hydroxide, a base. Just like hydrochloric acid, which donates a proton, carboxylic acid donates this proton, react with hydroxide, forms water molecule, and the rest is called carboxylate. So just like hydrochloric acid react with sodium hydroxide, forms water, at the same time it has sodium chloride. Here the carboxylate with the sodium, that's a salt. If carbonyl carbon is attached to oxygen and another alkyl group instead of hydroxide, okay, if it's hydroxide, that's a carboxylic acid. If oxygen and alkyl group, that is a ester. The ester group is formed by the reaction of alcohol and a carboxylic acid. So the hydroxide from carboxylic acid and the hydrogen from alcohol combine, forms water, and the rest of alcohol goes to the carbonyl carbon and forms the ester. Okay, ester groups occur commonly in lipids, which are formed by esterification of fatty acid. So this reaction is called the Fischer esterification reaction. A carboxylic acid, a alcohol, forms ester. This R, okay, comes from carboxylic acid, and this R prime, comes from the alcohol. We just showed esterification reaction where a carboxylic acid and alcohol to give an ester and water. The reverse of this reaction, where an ester react with water to go back to carboxylic acid and alcohol, is called ester hydrolysis. So in larger amount of water, the carbon-oxygen bond in ester is broken, and hydroxide replace OR, alkoxide group. Okay, goes here to form the carboxylic acid. Now, if instead of water we add sodium hydroxide, a base, then the carboxylic acid immediately react with this base to give you the carboxylate with the sodium, okay, to form the salt. And this reaction, okay, the hydrolysis using sodium hydroxide is called a saponification reaction. This is the process used to make soaps from lipids. So here shows a glyceride molecule which contains R group. Okay, so the R is a very long chain, so maybe carbon 16 or 17 or 18 or even 20, so very long chain of carbon. Okay, this is a carbonyl group, and OR, so that's the ester. So you have another one, this one, and this one. So one triglyceride contains 3 ester groups. When triglyceride treated with sodium hydroxide, it gives you 3 ester carboxylate. So this is a carboxylate. Carboxylate, carboxylate. Remember, R is a very long chain. So this part is hydrophobic, means it does not like water. But the other part, this carboxylate part, likes water, so it's hydrophilic. All right. So the same molecule has 2 parts. One likes water, one dislikes water, and it's a soap molecule. Okay. So a glyceride saponification reaction gives 3 soap molecules. When the carbonyl carbon is bonded to a nitrogen, the functional group is called amide. Compare with amine. Well, a alkyl group, for example, CH3 is attached to a nitrogen. So that's amine with no CO double bond. In amide, there's a CO double bond, and the carbonyl carbon is bonded to a nitrogen. Amides, like esters, can be hydrolyzed to give a carboxylic acid and an amine. So here shows the hydrolysis of ester. So ester with water go back to carboxylic acid and alcohol. Similarly, if it's a amide, so R, CO, okay, and let's say this is H, this is another alkyl group, let's say CH3, so that's an amide in water, okay, hydrolyze, and that will give, so with acid condition, and that will give you carboxylic acid. Okay, so you see this bond break, hydroxide from water replace the nitrogen part, and that gives you carboxylic acid, and the rest is an amine, so NHCH3 with a hydrogen. Okay, so it hydrolyzes back. However, amine is a weak base, and carboxylic acid is an acid. So acid base will react. So this will continue react to give you a ammonium salt. If you want to keep amine, then the reaction condition has to change from acidic condition to basic condition. For example, sodium hydroxide. So if we use sodium hydroxide, then the product carboxylic acid will not react with amine. Instead, it will react with sodium hydroxide. And these two will give you the salt. So carboxylic acid becomes carboxylate, so O negative, and sodium. All right, and then you have amine here. Okay, so the amide hydrolysis is usually done in basic condition, give you amine with sodium carboxylate. Okay, the peptide bond which links amino acid in a protein is an amide group. Sample problem 15.6. Predict the products of the following reactions. So to answer this question, we need to identify the functional groups in the reactants and see how they change. So in A, we see carboxylic acid group, and we see an alcohol. And we know carboxylic acid and alcohol undergo esterification reaction. So the alcohol part, okay, go here, replace or substitute for the hydroxide to give an ester. So in B, we see amide, so CO double bond with nitrogen. In water, it will hydrolyze back to the carboxylic acid and amine. Now, because we have a base, so the carboxylic acid should react with base to give you sodium carboxylate. So the final product should be sodium carboxylate plus an amine. Here shows the answer keys. So in A, the ester is formed. So the alcohol part, okay, substitute the hydroxide, give you the ester, and the hydroxide and this hydrogen forms water. In B, this bond break, so this part come out as amine, and the other part forms carboxylic acid, which react with sodium hydroxide to form sodium carboxylate. Hydrocarbons containing carbon-carbon triple bond are called alkynes. Alkynes, like alkenes, undergo addition reactions. So one hydrogen molecule can add to a triple bond of an alkyne to form a double bond alkene. Another hydrogen molecule adds to the double bond to make an alkane. CN triple bond is called nitriles. Nitriles are made by substitution reaction of alkyl halide with a cyanide. So sodium cyanide in solution forms sodium ion and cyanide ion. And the cyanide ion has a CN triple bond with a lone pair electron in carbon. So this lone pair electron attack carbon, replace chlorine, and forms nitrile. Sample problem 15.7. Circle and name the functional groups in the following molecules. A. Here is a carbonyl group with a hydroxy. So that's a carboxylic acid. Another carbonyl group, one side carbon, one side oxygen with a carbon. So that's an ester. Here you have a benzene ring, which belongs to a ring, okay, an aromatic compound. Next one, we see a hydroxy connect to carbon. There's no CO double bond, and that's an alcohol. Okay, here is a nitrogen connect to carbon with no CO double bond, so that's an amine. Again, there's a benzene ring, so a ring. Okay, next one, CO double bond, both sides are carbon atoms, so this is a ketone. A chlorine bonds to carbon with no CO double bond, carbonyl carbon, connect to this. So that's an haloalkene. Alkane, okay, haloalkane. Now there's a double bond here, that's an alkene. Here shows the answer keys for sample problem 15.7. Let's summarize the important functional groups in organic compounds. We started with the functional groups that contain only single bonds. Okay, these are here alcohols, haloalkane, amine. So in alcohol, a carbon bonds to an oxygen with hydrogen. In haloalkane, carbon bonds to a halogen atom. In amine, a carbon bonds to a nitrogen. These functional groups usually undergo elimination reaction and substitution reactions. Okay, carbon-carbon double bond called alkene, okay, ENE, and carbon-carbon triple bond called alkyne. So these functional groups usually undergo addition reactions. CO double bond is called carbonyl. When the carbonyl carbon bonds to one or two hydrogens, it's called aldehyde. When the both sides of carbonyl carbon are carbon atoms, no hydrogen attached to the carbonyl carbon, the functional group is a ketone. Okay, when carbonyl carbon bonds to an oxygen with hydrogen, hydroxide, and the functional group is called carboxylic acid. So this proton can be donated to react with a base. When carbonyl carbon bonds to an oxygen with another alkyl group, okay, carbon, and that is called ester. When carbonyl carbon bonds to a nitrogen, and that's called amide. Carbon-nitrogen triple bond is called nitrile.